Okay, last time on 13.3, we end up with this TNB frame, but we don't have any example on that yet. Like I plan to do some example on the tangent and normal and binormal unit factor now, and I would also like to do some examples on rectifying planes, osculating plane. Okay, it's not that it's super important in the progress of our course, but it's one aspect that you would like to know, you learn uh, as the use of our calculus here. Okay, let's see. In this, I pick questions from this, our textbook number 48. Number 48, find the factors t and b at the given point 1, 0, 0. Okay, let's remind ourselves what is unit tangent factor. Unit tangent factor is defined to be r prime t over the magnitude of r prime t. So, and then unit normal factor is the derivative of unit tangent factor divided by its own length again. While binormal unit factor is t cross n. Okay, now let's apply that here. In number 48, we have RT equals to that. So what is R prime T? R prime T will be negative sine T cosine T. Oh, what is the derivative of natural log of cosine T? That's 1 over cosine T times the derivative of cosine T, which will give us negative sine T for that one. So this will be negative tangent T. Okay. You know what? What is the time? What is the T to get that 1, 0, 0 though? I backtrack a little bit. We need to find T such that RT equals to 1, 0, 0. Okay. I think what I will do is I match the x component cosine t equals to 1. That implies t must be multiple of 2 pi, right? Integer multiple of 2 pi. And sine t equals to 0. It means t is multiple of pi, right? Okay, and then I think the last one is the one we really need. Natural log of cosine t equals to 0 means cosine t equals to 1, right? So t is equals to 2 pi k. Okay, so from there we find out that t, the time must be 2 pi k, where k is an integer. Okay, we may say that t equals to 0, but it actually no, it's multiple value. There are a lot of time t that give us that coordinate. Okay, there are a lot of time t that give us that coordinate. Okay, then from here we see what is r prime of 2 pi k. Actually, you can see that cosine t at that time is 1, sine t at that time is 0, right? So we just use that though. We just use that. So negative sine t. At that time, t is 0, cosine t is 1. Now the thing is, what is the tangent? The tangent is 0, huh? Okay. And the magnitude, therefore, the magnitude of r prime of 2 pi k is just 1. Therefore, unit tangent factor at 2 pi k is equal to 0, 1, 0 divided by 1, which is itself 0, 1, 0. Okay, now next, how about unit normal factor? So I take that, I need to find that the unit tangent factor function first. Unit tangent factor functions, oh shoot, I need to find the length here, huh? So the length of r prime t is square root of negative sine t squared plus cosine t squared plus negative tangent t squared. That is square root of the first two terms give us 1 plus tangent squared t. That is secant, huh? That's square root of secant square t, which is absolute of secant t, just to make sure that it gives us a positive value. Okay, so the unit tangent factor is given by, the unit tangent factor is now given by negative sine t cosine t negative tangent t over absolute of secant t. That will give us secant. So basically I multiply everything on the top by cosine, huh? So this will be negative sine t cosine t. This is cosine square t. This is negative sine t. Okay. Now then, when I take the derivative, what will the derivative of negative sine t cosine t? That will be this will be negative cosine t times cosine t minus, this comes plus sine square t. Cosine square t, when I do the derivative, is negative 2 cosine t sine t, and this is negative cosine t. So this will be negative cosine 2t, negative sine 2t, and cosine t. The magnitude of t prime t is, actually I don't need to, huh? I don't need to. I just plug in one right away. I plug that in right away, right? T prime 2 pi k, right? Yeah. T prime 2 pi k. And actually, I don't need this. I don't need this. Sorry, I'm working too hard. And I will use the fact that we know the value of cosine t, which is what? The value of cosine t is 1. So this is negative 1 plus 0, comma, this is 0, and then this is negative 1, right? That gives me negative 1, 0, negative 1, whose length is square root of 2. Therefore, unit normal factor is now at 2 pi k is now negative 1 over square root of 2, 0, negative 1 over square root of 2. Now then, let me go back here. What is about my unit binomial factor at 2 pi k? That is t cross n. I just need this, right? Which is the I, j, k, and then 0, 1, 0, negative 1 over radical 2, 0, negative 1 over radical 2. And actually, if you think about it, let me just do it here. Because you need this skill anyway, even though it is more appropriate for you to learn that in linear algebra, maybe. I can factor that negative 1 over radical 2 out. Okay, because we have common factor on that row, right? 0, 1, 0, 1, 0, 1. Now then, this will give us negative 1 over radical 2, 1, 0, negative 1. Okay, so what happened is this is the unit tangent factor, this is unit normal factor, and this is the unit binormal factor. Okay, now through this question, this long here, the work actually very long. You may not get used to it yet, but I need you to be aware with that. Okay, that's for number 48. Let's go on with the next one, normal plane and then osculating plane. We review a little bit what is normal plane. Normal plane is normal to unit tangent factor. So if I work on number 50, our r t equals to t squared t cubed at time 1, right? That's the only way. R1 equals to 1, 1, 1. Okay, so r prime t equals to 1, 2t, 3t squared. The magnitude, no, before that, let me plug in 1 first. So r prime 1 equals to 1, 2, 3, whose length is square root of 1 squared plus 2 squared plus 3 squared, that's square root of 14. So the unit tangent factor at time 1 is 1 over square root of 14, 1, 2, 3. Okay, now notice that this is actually parallel to 1, 2, 3. Is it right? So the normal plane, which is normal to tangent factor. Okay. Now at t equals to 1, now that normal plane, no, not writing it there. Oops, sorry. That normal plane is normal to is normal to 1, 2, 3 at 1, 1, 1. Okay, so the normal plane is given by is given by 1x plus 2y plus 3z equals to constant when I plug in 1, 1, 1, the coordinate, 1 plus 2 plus 3 equals to D. So the equation of normal plane mm, 6 equals to D. The equation of normal plane is x plus 2y plus 3z equals to 6. Next, what is osculating plane? We know that osculating plane is normal to binormal unit vector at time 1 later on, right? Okay, but we still need to find so from here we have the magnitude of r prime t is square root of 1 plus 4t squared plus 9t to the fourth. Therefore, unit tangent factor at time t is 1, 2t, 3t squared over that ugly number, ugly expression. Now I need to do the derivative. Okay, I need to do the derivative. Then you see how painful this can be. Okay, I will see the t as the function of t, which is 1 over the denominator times 1, 2t, 3t squared. Okay, so t unit tangent factor prime will be f prime t times 1, 2t, 3t squared plus ft times the derivative of this is 0 to 6t. Now, what is f prime t? The derivative of that function, ft equals to 1 plus 4t squared plus 9t to the 4 to the power of 1/2, so that the derivative will be 1/2 of that guy to the power of negative 1/2 times the derivative of that thing, which is 8t plus 36t cubed. It's quite ugly, huh? So it will be 8t plus 36t cubed over 2 square root of 1 plus t 4t squared plus 9t to the fourth times 1, 2t, 3t squared plus 1 over, oh, hold on, this is negative, so this is negative 3/2, my bad. This is negative, yeah, so I need to do this, sorry, this is to the power of 3/2 here, plus 1 over 1 plus 4t squared plus 9t to the 4 to the power of 1/2 times 0 to 6t. Now the nice thing is we just need to observe that at 1, right? We just need to observe that at 1. If we try to observe that at 1, I basically plug 1 in, I get negative of 44 over 2 times 14 square root of 14, 1, 2, 3, plus 1 over square root of 14, 0 to 6, because the t is 1. what I get here is I cancel the 2, 22, 11 over 7 square root of 14 times 1, 2, 3 plus 1 over square root of 14, 0 to 6. It's kind of nasty, huh? Okay, hold on. So this is equal to, if I put things together, let me factor that 1 over square root of 14 out. So inside I have negative 11 over 7 plus 0. And then negative 22 over 7 plus 14 over 7. And then negative 33 over 7 plus 42 over 7. 1 over square root of 14, negative 11 over 7, this is negative 8 over 7, and this is positive 9, positive 9 over 7. Notice if I factor that 7 out again, you will see that this T1 prime 1, so the unit normal factor at 1, will be parallel to negative 11, negative 8, 9. Okay. To be more precise, let me move this a little bit. To be more precise, our unit normal factor at time 1 will be 1 over 7 square root of 14 of that factor. This is the T prime 1, right? Divided by its length. But when we divide by the length, notice that you will see the length is 1 over 7 square root of 14 square root of negative 11 squared, negative 8 squared, 9 squared, like that. Okay, in which the coefficient cancels, right? Negative 8, 9. Okay, and then here we have 1 over square root of a big number, 121, and then 81, and then 64. What's that? 14, 16, 1, 266. Square root of 266. I don't know if I make any miscomputation though. I hope not. Okay, I just keep on going. But I know technically I'm correct unless I make some miscomputation. Okay. But this normal factor here is now parallel. We can just say this is parallel to negative 11, negative 8, 9. Okay, now why? Because our binormal factor at 1 is equal to ijk of normal factor, tangent at 1. Let me mark it. Tangent at 1, okay, which is, let me factor 1 over square root of 14 out, and 1, 2, 3. And then normal factor at 1, let me factor 1 over square root of 266 out, and then I get negative 11, negative 8, 9. Okay. And what we need is actually the factor normal to the osculating plane, right? Okay. We just need a factor normal to osculating plane. It doesn't have to be the unit binormal factor. Anything parallel to that will be good. Okay. So this is 1 over square root of 14, square root of 266, and then it will be 18 plus 24. What's that? 18 plus 24, that's 42. Right, and then 9 plus 33, that's 42. That's negative 42 because that's the second component. And then the last part is negative 8 plus 22. Negative 8 plus 22, that's 14. Okay, in fact, I can factor 14 out from there, right? Okay, so I can factor 14 out, so I get square root of 14 on the top over square root of 266. I can simplify that further. Okay, 3, negative 3, 1. Okay, so that's 9, 18, 19. Is 14 times 19? It's 266. Yeah, huh? Okay, because by normal unit factor is unit, right? So because the length has to be unit, so the length here is square root of 19. Then I suspect this is 1 over square root of 19. That's how I think. Okay, that's how I think. But what we need is actually not the actual value of that binomial factor. I just need a factor normal to it. So osculating plane that we are looking for is actually normal to that 3, negative 3, 1. Okay, long work, huh? Okay, so the equation will be 3x minus 3y plus c equals to d, and then I plug in 1, 1, 1. That's the coordinate on that plane. 3 minus 3 plus 1 equals to d, so d equals to 1. So the equation of the osculating plane is 3x minus 3y plus c equals to 1. Okay. Next, the next part that we need to go over, which we didn't go over there last time from that 13.3a, I believe at the beginning I show you that we did the arc length and reparameterization. We did the TMB frame. I am still missing the curvature. Let's talk about curvature now. There are some definition of curvature. Let me first give you the geometric interpretation of curvature. Okay, curvature at time t denoted by kappa, not k, not k. So maybe you think of that. It's supposed to be Greek letter k, Greek letter kappa, but it looks like an italic k, capital K, but small size. Okay, now you can see this geometrically as the reciprocal of the radius of the circle best tangent to a curve C at time t. Okay, so imagine you have a curve like that. Okay, at this point here, can you imagine what is the radius of the circle fit that best? And it has to be a circle. So let's say this is the circle that fit that best, right? Okay, now then if this is the radius is A. Okay, so we have the tangent line, right? Okay, think of this circle as tangent circle. Now, the radius of that tangent circle is the reciprocal of the curvature. Okay, so the curvature at that point is equals to 1 over A, which is the radius of that circle. Okay, now you will see then the larger the radius, the smaller the curvature. So if you have a straight line, then the circle that fits the tangent to that straight line must have radius infinity, right? The radius must be infinity. Therefore, the curvature must be 0. Okay. In other words, if the curvature is 0, basically at that point, at this point here, the curve is not bending, it's straight. Okay. On the other hand, if the curvature is very big, it means the radius is very small. If the radius is very small, it means you are turning very sharp. So let's say you have this, right? And then the circle that fits there, tangent circle fits there, is this one. You will see then the curvature will be the reciprocal of that circle, the radius of that circle. Okay. Now that's the first interpretation. Of course, that's just the idea so far. Okay. Oh yeah, curvature is the reciprocal of the radius. But how do we compute that? Okay. How do we compute that? Then we come up with a definition. We come up with the definition. The curvature at time t is defined to be the magnitude of dt respect to ds. I know. What is that again, Thomas? Here's the thing. It's so hard to compute this, though. It's so hard to compute this. In other words, this formula is very not applicable. What we are going to do is try to come up with a formula from here. We will derive this formula even further to get a formula that we can use. Okay? And one of them is to apply chain rule, where we rewrite dt times dt ds. Right? That's basically chain rule, which we can split to be the derivative of unit tangent vector respect to time, the length of that divided by ds dt. Okay? Divided by ds dt. Now you will see that ds dt is basically the change of distance traveled over time, which in the past, if you go back to the earlier discussion of 13.3, you will see that ds dt is basically the magnitude of r prime t. Just to remind you that the arc length equals to integral of the magnitude of r prime t dt, right? In other words, the differential of s equals to magnitude of r prime t dt, and therefore we can rewrite the magnitude of r prime t dt, r prime t, as ds dt. Okay, now I think this formula is a lot more useful. Yeah, I think this formula is a lot more useful. If I will not derive this formula, but you can take a look in the book in the next one. Our textbook says, from our textbook, we have that the curvature of t, this formula is very applicable already, okay? But if you remember in our example above, we really have hard time to find normal factor, right? The t prime t to do derivative of that thing is ugly, right? Okay, to do derivative of this is ugly. To get this one, wow, it's painful. Okay, so is there any way for us to get a better formula? The formula may be longer, but more applicable. Okay, not that tedious. Like this formula seems to be short, but to apply that is tedious. Okay, now our textbooks say that curvature can also be computed using this formula. That is the magnitude of r prime t cross r double prime t over magnitude of r prime t being cubed. Okay, now because there will be some questions in our textbook regarding where you use this, I will derive this formula. Okay, I will derive this formula, and I hope you practice also at home on how to use this formula. Proof. Before I really work on that formula, I want to make a statement first. Note that if you have a factor function, call that RT. No, I don't want to use RT. I want to use another factor function. Oh, you know what? Let's just do it this way. We want to say that the derivative of unit tangent factor is always perpendicular to the unit tangent factor. Okay, think of it this way. If this is the curve, okay, this is the r prime t at this point, that's the tangent factor, right? Now we know unit tangent factor has length 1. Okay, has length 1. Now, the change of unit tangent factor, let me use black color, is always perpendicular to that unit tangent factor. T prime t is perpendicular to t. Okay, now how do we prove this? Proof. So inside this proof, I prove this statement first. Proof. Now, notice that unit tangent factor must have length 1. Therefore, the square of that also has length 1. Actually, we don't need the length to be exactly 1. We just need the length to be constant. You will see this formula works even when the length is constant instead of just 1. Now, on the other hand, the magnitude of a factor being squared is the same to that factor dot to itself. Right? Now, I will do implicit differentiation here. That gives me t prime t dot t plus t unit tangent factor times dot the derivative of unit tangent factor, that should be 0. But that simply means 2 times unit tangent factor dot t prime t is equal to 0, which means unit tangent factors and dot the derivative of that unit tangent factor is 0, which implies those two factors are normal to each other. Okay, now we will use this result later on. Now, next, we know that unit tangent factor at the same time is equals to r prime t divided by the magnitude of r prime t. Okay, which we define as let's call it this way then. R prime t therefore is equal to ds, maybe I call it this way first, magnitude of r prime t. You know that even though this is a factor, because it's magnitude, it becomes scalar, multiplied by unit tangent factor t, right? Which I can call this ds dt. Remember that? ds dt times unit tangent factor t. Okay, therefore the derivative the r prime t, r double prime t will be the second derivative of ds dt, the next derivative of ds dt times unit tangent factor plus ds dt times t prime t. Okay, give me a second. Okay, now so we have the second derivative of RT looks like that right now. I know it's still painful. It's still painful. Our goal is actually to get rid of this. Okay, because t prime t is ugly. In fact, if possible, we don't even want to find unit tangent factor. It will be a lot easier if we can express our curvature later on in terms of r prime t and r double prime t. That's our goal. Okay, now let's go on. The thing is, in our next section, I will still use this formula though. So you may want to put a star here. Okay, we will quote this formula later on. Now, the following is a very nice trick. A very nice, what you call that? Yeah, a trick. How to get rid one of the terms here. Notice that this guy is perpendicular to this guy. Okay, so if you think about that, let's say this is RT, right? And this is the velocity, the r prime t. Now you will see that r double prime t actually looks like this. Okay, this is the r double prime t, which consists of the scalar multiple of unit tangent factor. So this is this, let's say this is the unit tangent factor. Okay, now the this, yeah, and then this is the scalar multiple of that, right? And also consists of the scalar multiple of t prime t. So let's say this is t prime t. Okay, now we have the scalar multiple of that. Okay, well, anyway, our goal is to find the curvature. But we will come back to this diagram in the next section. What I will do is I will multiply, I cross r prime t by r double prime t. Now, r prime t is ds dt unit tangent factor, right? This one here. Okay. Multiplied by, actually cross this guy. Let me copy paste that. Which is equals to ds dt d squared as dt squared, the second derivative, of t cross t. That's for the first term, right? Plus ds dt times ds dt of unit tangent factor cross the derivative of unit tangent factor. Oh shoot, this is painful, huh? Now the thing is, this guy is equals to 0. This is equals to factor 0. Why? Because the cross product of two parallel factors is 0. Okay, so we end up with only ds dt being squared times unit tangent factor at time t cross t prime t times. It doesn't look much better. Well, it's a bit better. It's a bit better. It's a bit better. Let's go on a bit further. If I do the magnitude here, then I will get ds dt squared times the magnitude of unit tangent factor cross the derivative of unit tangent factor at time t. Now, but since unit tangent factor is normal to the derivative of unit tangent factor, which means the angle between them is 90 degrees, so the magnitude of the cross product equals to the product of the magnitudes. It's supposed to be like this. It's supposed to be this guy times this guy times sine the included angle, but the included angle is pi over 2, right? Which is equal to 1. Okay? Okay, maybe I write it that way first. I will move this below and then call this sine theta, right? And theta equals to pi over 2. And we know that the length of unit tangent factor is 1. That's why we call that unit. Therefore, the cross product of r prime t and r double prime t has a magnitude of ds dt squared times magnitude of t prime t. Okay, therefore magnitude of t prime t is the cross product of r prime t by r double prime t divided by ds dt squared. But ds dt is the magnitude of r prime t. Now, the curvature at time t is the magnitude of unit tangent factor prime divided by the magnitude of r prime t. So basically we divide that expression here, we divide this by another r prime t, which will then give us, becomes cube here. Now, this formula is very applicable because what? Basically, once you have RT, you just keep on doing R prime T and R double prime 3T, and then you can work on this, the curvature already using this. Okay, in fact, our textbook also mentioned what happened then if you have only 2 dimensions. If we only have 2-dimensional curve, can we compute the curvature? And the answer is yes. In 2 dimension, we have only, usually we have y as a function of fx, right? Okay, it's only 2 dimension. Now then you do augmentation. Maybe before I say augmentation, we do parameterization first. RT equals to x fx. So our parameter, instead of t, we use parameter x. Okay, now when I say augmentation, I refer to you extend this 2 dimension to 3-dimensional but on xy plane. Okay, now therefore From here, we have r prime x will be 1 f prime x 0, and r double prime x is 0 f double prime x 0. Okay, now the magnitude of r prime x is square root of 1 plus f prime x squared. Okay, while r prime x cross r double prime x will be the ijk thingy. Let me just do it fast. So it will be 0 here, it will be 0 here, it will be f double prime x here, whose magnitude is basically f double prime x. Of course, I'm supposed to use absolute sign though, because it's the magnitude. Therefore, in two-dimensional, the curvature at x will be given by absolute of the second derivative of x divided by the square root of 1 plus the derivative of fx squared. Okay, now that's a long proof, huh? This is a long work. So just to do the curvature, we actually did start from here, huh? Let me mark it. Yeah, the curvature work start from here. So it's a long note, a long proof. And notice that we don't do any computation yet. We don't have any example yet. Let's do one. Let me see if there's any question I can use. Hold on, give me a second. I picked a question earlier. So let's say I use this one here. Number 22 from our textbook. We want to find the curvature. Find curvature at time t. We already have rt, so r prime t will be 1 to t e to the t. And r double prime t will be 0 to e to the t. Okay, now the magnitude of r prime t is square root of 1 plus 4t squared plus e to the 2t, while r prime t cross r double prime t will give us 2t e to the t minus 2e to the t. That's for the first component. The second component will be negative e to the t. And the last component is 2. Okay, so the magnitude of that will be, I know it's kind of messy. Imagine if we need to find the unit tangent factor and then need to do the derivative. It's extremely painful, right? So I have 2t e to the t minus 2e to the t squared plus e to the 2t plus 4. That will be 4t squared e to the 2t minus 8t e to the 2t plus 4e to the 2t plus e to the 2t plus 4. Simplify that. I wonder what we get. Square root of 4t squared e to the 2t, and then minus 8t e to the 2t plus 5 e to the 2t plus 4. Okay, so the curvature will be, the curvature at time t will then be this ugly square root here, and I don't think I can factor anything out, huh? 4t squared e to the 2t minus 8t e to the 2t plus 5 e to the 2t plus 4 divided by the cube of this. Okay, I know it looks very nasty, huh? But yes, that's the curvature. Okay. The suggested homework from here. From this 13.3, the second part B, where we do some example on TNB frame and then the curvature 17 to 25, 43, 45, 47, 49. That's for this 13.3, the second part. Okay, right now it's 5:41. We will come back at 5:51 to continue with the next section, 13.4. The next section we will work on is section 13.4. That is on motion in space. Basically, we work with RT, the curve RT, okay, and then we will work on the velocity and then acceleration vector functions. And then from there, we will also look at the tangential and normal component of vector functions. And from there, we will do one, it's not a project, but we will focus on one case, which I think will be useful for you if you are going for a projectile motion, basically. Okay, so this is a special case projectile motion. This is the basic if you are going for defense where you work on missiles. Okay, we will spend some time, a significant amount of time on projectile motion toward the end. But let's start with motion in space with the knowledge that let RT be the curve, right? We call that position vector function. So let's say that's a trajectory in space. Okay, now our R prime T will be called velocity vector function. If you remember in Calc 1, we learned, I think we learned ST as the position on the number line, position at time t. And then S prime t, we call that velocity function, right? How fast it actually moves. And of course, it has positive or negative direction. And then the next derivative, we call that acceleration. And we call that, the notation is AT. Okay, but because we apply that in one-dimensional number line, then we don't need to use factor notation, right? Okay, that's in Calc 1. Now, in Calc 2, in Calc 3, the velocity vector function is a factor, okay? So when we rewrite that as a V notation, don't forget you still need to use that factor notation, okay? That's the velocity vector function. Now, velocity has direction, that's why we call that factor. Now, the one that doesn't have direction is the magnitude of that, which in the previous section, we write that as r prime t. Okay, now because it is scalar, we will write that as Vt. Okay, so at this point, note that V prime t is not the same to Vt. Okay, note that these two are not the same. Why? One of them is a factor, the other one is scalar. In fact, we will call this speed function. It's scalar, no direction. No direction. Okay? And then the next derivative of that r prime t is called acceleration vector function. It's acceleration vector function. Okay, now suppose for example we have a curve C given by RT, the position vector function, t squared, 5t, and t squared minus 16t. Then the velocity vector function will be 2t, 5, 2t minus 16. Okay, now then the speed function Vt, no factor, is the magnitude of that. Okay, which will give us square root of 4t squared plus 25 plus 4t squared minus 64t plus 256, which will be square root of 8t squared minus 64t plus 281. Okay, that's the speed function. Of course, once we get the speed function, we may ask this question, find the minimum speed. Okay, find the minimum speed. And basically, we need to first find when will, at what time t, Vt is minimum. Right? Basically, once we find the t, we plug that t into the Vt, we get the minimum speed. Okay? And we can do it this way. Notice that Vt is minimum. Notice that it is inside the square root when the radicand is minimum. 8t squared minus 64t plus 281 is minimum. Right? And from quadratic equation, we know that a parabola has minimum point when the t equals to negative b over 2a. So you will see t equals to 4. Therefore, the minimum speed happens when the t is 4. 8 times 4 squared minus 64 times 4 plus 281. Okay, so how to do this? This is negative 128 plus 281. So the minimum speed is, oh, it's actually pretty fast, huh? So that will be 3 here, 5 here, 1 here. That's the minimum speed. Okay. Now, of course, another way to find when will this minimum is you do the first derivative, right? So 16t minus 64, you set it equals to 0. But doing so, when you do the first derivative, it may be just it just gives you an extreme value, or maybe it's not the maximum, not minimum. You see what I mean? Like, because your curve may look like this, that's the first derivative is 0 there, that's the maximum. Maybe like this, that gives us the minimum, which is our case here. But we may have a situation like this, which is not the maximum minimum. That's why I prefer not to use that for this kind of question, because we have a more foundational method by recognizing that we were dealing with a quadratic function, right? Quadratic function, it's a parabola opens up, therefore we have minimum value, and the minimum value happens when negative b over 2a. Okay, now finally, what is the acceleration vector function? We do the further derivative from the velocity vector function, that's 2, 0, 2. Okay. Next one. Remember we talked about the acceleration, the tangential and normal component of our vector functions. I have that picture somewhere here. Here. No, this one here. Let me grab this and copy that and then put here. So we will talk about next the tangential and normal component of acceleration. Let's see how do we actually use this though. Now, before, oh, I forget the curve. Let me do the curve. Let's say the curve looks like, let's say the curve looks like this. Yeah, let's say that's the curve. Okay. Now remember I used the illustration of a car before, right? If this is your car traveling at this point, and then on this path, and then this is your r prime t, and we say that r prime t basically the direction of your headlight if you are driving a car, right? Okay, now let's imagine if we are, instead of dealing with a car, we actually ride a motorboat. It's like what you call it, jet ski, is it the right term? jet ski. Okay, so basically what happened is there could be times that you travel along this path, right? But then your jet ski is actually facing that way. Your jet ski is actually facing that way, but you are drifting in that direction. Can you imagine? Okay, that happens with the airplane. That happens if you actually travel on fluid dynamics. Okay, on a fluid, like maybe the air or maybe water, on the sea, on the ocean. Okay, so you are on the ski or you're on a boat. Your boat is actually facing that way, but it's actually drifting in that direction. Now, then this will be the r prime t, and this is our r double prime t. Okay, so we come up with this kind of picture here. Okay, now the thing is we want now to rewrite our acceleration as the tangential component of unit tangent factor plus the normal component of unit normal factor. Okay, from that picture you already have this is the unit tangent factor here, right? Do you see this one? Okay, now our unit normal factor maybe something looks like let me use slightly different color. Maybe something looks like this. Maybe this is our unit normal factor. Okay, what we are interested in to find what the compared to the unit tangent factor, what do we need to multiply it? How many times of the unit normal factor is the length of this guy here? This is the length of this guy here is basically the R8AT. Okay, that's the length. And the length here is our A sub n, the normal component of that acceleration. Okay, now, but if we look back, the tangential component is basically, this is where supposed to be easy for you. The tangential component is basically the absolute of the component of r double prime t on r prime t. Is it right? Which, according to what we learned in the past, the component of r double prime t onto r prime t is r prime t, the dot product of those two factors, divided by the magnitude of r prime t. Okay. While the normal component, okay, it's basically this part here. It's this part here. Imagine if we have this parallelogram, we need to find the height, right? We need to find the height. So what is the height of that parallelogram? The height of parallelogram equals to the magnitude of the cross product divided by the length of the base. Okay. Now, why is this important? What is this important? Now, I want you to imagine one case, for example. For example, when you are constructing one day, I hope you do, or one of you do. Suppose you are constructing on a freeway, like you have a loop, right? You have a loop on a freeway. Let's say from one freeway you need to go to another freeway. You have a junction, right? So you have a loop, like a curve there, and you have a car here. Now you imagine, suppose the phi prime, imagine if that person's actually imagine if that person is actually traveling at the speed of 65 miles per hour on that loop, on that turning, on that junction. Okay, then the question is, will that be safe? Okay, so from that phi t, you try to find out what is the velocity vector function. Okay, using that velocity vector function, can you find the acceleration vector function? Now, why is it important? Why is it important? Because the fact is, this car, if we're going too fast, this car may be thrown away, thrown outside of that freeway because it's running too fast. And the way we found out if it is too fast or not is by finding the normal component of that vector function. Okay, normal component of that acceleration. Okay, and can the four tires of that car sustain the force of throwing it away? Okay, if the force is too, how do we know that the force is enough? Then you need to see if the normal component of that acceleration that is generated from four tires, okay, is actually larger than how much you will be thrown away on that curve. Okay, what you don't want to happen is like you turn so sharp and so fast and you get thrown out from the freeway. That's one. Okay, but the worst part is like maybe you are not thrown out, but you actually flip out. That's the case with trucks, right? If you have a truck, you see the mass is very big, right? And it actually on that curve, it turns too fast, it will flip. It will flip. Okay, so what we learn here has something to do with that. Okay, what we learn here has something to do with, and of course, if one day you are actually designing a missile, right? Which I believe that's what we really need right now. Why do we need that? Not that we need that for a war, no, but we don't have sufficient people actually working in the to work with the weaponry right now. Okay, what you don't want to do is like you create a missile. Now you know why intercontinental ballistic missile or the scramjet is so hard to develop. Scramjet is flying very fast, very fast. It's so fast that it has to be straight. It's almost the trajectory almost straight. Now, what's wrong if it is not straight? Well, because imagine if you have a missile or let's say a body, a straight body like this, right? But then because of the curvature, maybe a small curvature with very high velocity, it actually breaks. Imagine you have a missile, okay? But the curvature is so big with the mass may be small, but the velocity is so big such that once it turns, it actually breaks. You know, so imagine if we are trying to send a missile to another country, right? The missile runs so fast and because it turns too sharp, it actually explodes midways. That's sad, right? Why? Because you may be able to create a missile or a ballistic that runs super fast, but that ballistic cannot turn. That's strange, right? So that ballistic, that missile, that bullet should be able to turn, okay? But the fastest that missile fly, the ability to turn actually get less, okay? Because if it turns too sharp, it may explode, it may break. Think that way, okay? The thing is, like, too many people actually going for something else that they think is interesting, but not enough people actually going to weaponry anymore. People who are going to weaponry, a lot of them actually from Air Force or the Space Force right now, okay? The thing is, like, people who go to Space Force or Air Force, they tend to be high school graduate, okay? If they're already an engineer, they tend not to go to be a service member, you know. While we need that there. I'm not for war, no. But the way I think is, like, if we have good weaponry, then we have less people, less country, less entity willing to make us their enemy. Okay, so in some sense, it actually contributes to the peace. Okay, so people think that have a weapon may induce some violence. No. I believe if you know I have some weapon on my body, I believe you will be more careful when you deal with me, right? Same thing with you. If I know you have some weapon on your body, like let's say you carry some knife, okay, I will be more careful when I deal with you. The way I talk to you will be a lot nicer. Does it make sense? Okay. So no, it's not about that weaponry negatively impact the peace process, though. It may be the other way around. Okay, and believe it or not, one of the reason that Iran, nothing against Iran, okay, I just talk about this from weaponry point of view, that no countries actually fight with Iran, but Iran's willing to fight with other countries is the fact that they have nuclear weapon. Okay. Yeah, and however dumb you think North Korean president, the leader of North Korean, Kim Jong-un, okay, we will not treat him carelessly simply because he has his hands on some nuclear weapon, even though we don't know if those weapons can actually reach the United States. Okay, but we still be more careful with that. Yeah, so my point is, if you have a good weaponry, chances are people will treat you with even better respect. Okay. Now next, I want to go on to the things that I consider very interesting, and I actually would like you to think about this even more, about projectile motion. Now, what is projectile motion? Projectile motion is the following, like this. Let me move this picture here and make it larger. Okay, I copy paste this picture from our textbook. Suppose we actually throw a stone. Okay, we throw a stone at the initial velocity v naught, the angle from positive x-axis alpha. Okay, and we have gravity g. Call that gravity g. So the gravity, the acceleration you will see is basically 0, negative g, because it's facing down, right? Okay, now what do we call projectile? Projectile is basically the thing that you throw at the beginning, but along its trajectory, there is no more extra force besides gravity. So we are not talking about missile. Like missile, when you shoot it, right? It keeps on pushing it though. It keeps on pushing it. Okay, so instead of only have gravity influencing the trajectory, the missile can actually change direction. You can turn it. Okay, but the foundation of learning the trajectory of a missile, trajectory of a satellite, maybe in future, starts from, suppose we have initial velocity. Suppose we have initial velocity at this point. But then once we throw this stone, for example, the only acceleration affecting that stone is only gravity. Then one of the big question is, then what is the range? How far will the stone actually land from the original place, the original point that we throw it? Okay, there are many questions though. There are many questions. The question that we have in our textbook for now is what is the range? And for example, what is the angle to maximize the range? Okay, if you want to throw a stone, what is the angle you throw it such that it reach the furthest? You can throw it very high, but you end up here, right? If you throw it too low, angle too low, it may land too early. Okay, so there's a trade-off in between, and you will see later on it's actually 45 degrees that give you the furthest range. Okay, but beside those, we also have questions like, okay, then suppose instead of like you want that to land there, let's say you want to shoot something in the air at that point, then what angle should we shoot it here? Okay, if we have a fixed initial velocity, usually that's a gun, right? Let's say you have a gun, you shoot the bullet, then the initial velocity is fixed, but at what angle should we shoot it such that it will hit that things in the air? Let's call that a drone, maybe. If you have a drone flying in the air, okay, then you ask yourself, if I want to stone that drone, okay, at what angle should I stone this drone? At what initial velocity such that it hits that in the air? Okay, what is the angle? And of course, another important thing is when it hits this drone, for example, or whatever item it is in space, at what angle it will hit it? Okay, at what angle from the horizontal it will hit it? That's another good question. Okay, or another one is at what velocity it will hit it. What you don't want to happen, for example, is you think you want to hit a drone at this point here. The problem is when this stone actually hit that drone at that point, the velocity is actually the minimum. You know, the velocity is actually minimum. Why? Because you have horizontal velocity, right? The horizontal component. We also have the vertical velocity, right? The thing is, at this point, the vertical velocity is actually 0. So the speed at this point is actually minimum. Now, what you don't want to happen is like you throw that drone so high, but by the time your stone actually reach that drone, the stone is actually barely touching it, but cannot damage it. Your stone come down, but the drone's still flying. You know, that's funny, right? You work so hard to find the angle so that you can hit that drone, but when you hit that drone, nothing happened to that drone. It's barely touching it. That's quite funny, right? Okay, so that's basically the big spirit of what we will do here. Now, of course, in other case later on, we will see what happened then if I throw that stone, or my projectile is actually not starting from height 0, but I start from certain height. Okay, and then let's say I shoot that at angle theta or angle alpha with initial velocity v naught. The question that where will that land? Now that gives us a scientific reason to argue that in case of war or in case of fighting, whoever can throw at a higher point from the higher point can actually have the further range. Okay. Now, so far we have those things mentioned intuitively. We don't have numbers attached to it. Okay. So a lot of us, when we were very young, when I was very young, I have ideas. Oh, we need to do this. We need to do this. We need to do this. Until my professor or our boss or the project says, you know what? Okay, you know what you need to do, but give the precise number, and nobody can come up with a precise number. You know, like you can throw a stone to a drone, but you still need to go more details. At what initial velocity, at what elevation, angle of elevation, okay? And when it hits it, will that break that drone, or will that simply touch it? Which is embarrassing, of course, right? Okay, now we will put details into this. We start with what we know. Suppose we have initial velocity v naught. Let v naught be our initial speed. V naught be initial speed, and alpha be our angle of elevation. From origin. In other words, we will throw, or the projectile will start from origin. Okay. So our initial velocity v naught, notice I use vector notation there, okay, which we can say this is v0 vector, velocity vectors at time 0, is actually equal to initial speed times cosine alpha, initial speed times sine alpha. Take a look at this. That initial velocity is basically how strong you throw it, right? The initial speed, but the x component is the cosine part, the y component is the sine part. Okay. And we have only gravity go against us. So the gravity at time t happens to be constant all the time, which is 0, negative g. I will purposely leave this gravity as g, using constant g, because on Earth, some people call that 10, some people call that 9.8. For now, I call it g. Of course, on the moon, it will be 1/6 of our earthly g gravity. Okay, now using these two, then can we find the velocity vector function, the general at time t in general? Now we know that this is actually integral of acceleration vector function. Okay, which when we integrate that, we will get 0, negative gt, right? Plus velocity at time 0. So 0, negative gt plus v naught cosine alpha, v naught sine alpha. Notice again, v naught without the vector notation is initial speed. Putting things together, we get v naught cosine alpha, comma, v naught sine alpha minus gt. Then how about the trajectory? How about the trajectory? The RT. What's the path of that projectile? Well, we integrate that Vt again. Right? When we integrate Vt, we will get V naught T t cosine alpha, phi naught t sine alpha minus 1/2 gt squared plus the place where you start. In this case, you start from origin. Okay, now suppose the starting point is not origin. Let's say you start at the height h, then it will be 0h here. Okay, if you start not, your initial height is not on the ground. If your initial height, let's say, is 100 meters above the ground, then it will be 0,100. Which, if we put together, it's basically the same factor we have earlier. Okay, now that's our trajectory. Now, so the question that we have, the first question we have here, this is example 5 in our book. Find the RT, and then what value of alpha maximize the range. So suppose we don't know the alpha yet. Okay, suppose we work with the general alpha. Okay, suppose we know the initial velocity, initial speed, and angle of elevation. Can we find the range? Can we find the range? The range is how far is it here? This is the range, right? How far it is here. But that's basically when it hits the ground again, right? When it hits the ground again. When it hits the ground again, it means the height is 0. Is it right? Okay. The projectile hits the ground when y equals to 0, right? When y equals to 0. Oh, so we need to find the t when the y equals to 0. And then we find, using that t, we find the x. That will give us the range. Okay? Now, let's see. Let's see. So when the y equals to 0, we get 0 equals to phi naught t sine alpha minus 1/2 gt squared, right? Okay, I factor the t. Let me factor 1/2 also out. So I get 2 phi naught sine alpha minus gt. That equals to 0. Okay, so either t equals to 0 or t equals to 2 phi naught sine alpha over g. Okay, which, if you think about it, is basically say the following. The projectile actually hits the ground at time 0, that's here, and the time 2 times the initial speed sine of the angle of elevation divided by the gravity. Okay, at that time it will hit the ground again. Okay, again, the context here is with initial height on the ground. So that's the time. Okay, so what is the range then? The range, actually, the x component at that time, which is phi naught times 2 phi naught sine alpha over g cosine alpha, which will give us 2 phi naught squared over g sine alpha cosine alpha. Let me make it nicer. This is phi naught squared sine 2 alpha over g. That's the range. if you throw that projectile, you release that projectile at height 0, then it will reach the ground again at this distance away from the initial point. Okay? Now, the interesting thing is, like, we can actually find how to maximize the range, right? The range is maximum. Range is maximum when, notice that the phi naught initial speed is fixed, right? Okay, the gravity we cannot change, but we may be able to change the alpha. At what angle should you throw that projectile? Okay, so the furthest distance we can reach is when sine 2 alpha is maximum, which is 1. But sine 2 alpha equals 1 when 2 alpha is 90 degrees, right? Therefore, when alpha is 45 degrees. In other words, if you try to throw something from initial point and on the ground, okay, and your initial speed is fixed, then the furthest distance you can go is by throwing it at 45 degrees. Okay. Another thing. Notice that the range here will be the same if you throw it at the angle that is complementary to each other. Okay, note, right? The range for alpha 1 equals to the range for alpha 2. There are two angles that give you the same range when alpha 1 plus alpha 2 equals to 90 degrees. In other words, if they are supplementary angles and complementary angles. Why? Because of the following. Sine 2 alpha 1 is equals to sine 2 times 90 degrees minus alpha 2. Think about that. Okay. In other words, if you throw it at 30 degrees and throw it at 60 degrees, you will hit the same spot on the ground. If you throw them at 20 degrees, it will have the same range compared to if you throw it at 70 degrees. 20 and 70 the same. Okay. Now, it has something to do with the fact that it's double the angle, right? Double angle. Therefore, as long as those two angles are complementary, the value of sine of 2 alpha are actually the same. Okay, so notice that from this one equation only, from this one formula only, we actually now can tell when will that give us the maximum range. And if you throw it at an angle other than 45 degrees, you can reach the same range. Let's say you throw it at 50 degrees here, you will reach the same range if you throw it at 40 degrees. Okay? Interesting, huh? Another thing we can talk about is at what speed, right? So we know that it will hit the ground there. It will hit the ground there. But can we tell at what velocity it hits the ground, and therefore at what speed it hits the ground? We don't want to have a situation where you throw something and that stone happened to just touch that person, and that person actually nothing damaging to that person, and that person can smile back to you. Okay, what's the point of throwing the stone if that's what you do, if that's what happened, right? Okay, so we want to make sure that when we throw it, when it hits that person or to hit the target, we know at what speed it will hit the target. Okay, now how do we compute that? Well, we know the time it will hit the target already, right? So the velocity vector function at that time, 2 phi naught sine alpha over g is equals to, where's the velocity? This is the velocity, huh? Right? This is the velocity. Notice that we have only one component t here, t component here. So the velocity will be phi naught cosine alpha, phi naught sine alpha minus 1/2, not 1/2, minus gt, huh? Minus gt, minus g times t. But when you compute this, you will get this is phi naught sine alpha minus 2 phi naught sine alpha, which is phi naught cosine alpha, phi naught negative phi naught sine alpha, right? Which, if you compare that with, when we compare that to the initial velocity, with initial velocity phi naught cosine alpha, phi naught sine alpha, okay, minus gt, but the initial velocity is when t equals to 0, right? Okay, notice that only the y component get the opposite. Right? Which, again, if you think about it, when you think about it, what is the velocity then here? The speed here, the speed at that time, the speed when it hits the ground, which is the time 2 phi naught sine alpha over g, the speed will be the square root of phi naught squared cosine squared alpha plus phi naught squared sine squared alpha. Boom, this is basically initial speed. In other words, when you throw, you have a projectile. When you have a projectile, you throw it here. Okay, the speed when it reaches the ground here, when it hits the target on the ground here, will be the same speed. It's just different angle. Okay, if the angle here is alpha, then the angle here will be also alpha, right? It will hit that with angle alpha. Does it make sense? In fact, you will see if this projectile actually traveled without any air resistance, then at any given height, you will see at any given height, the velocity here is the same with the velocity here. Okay, and this is actually being considered, how to say that, it's considered correct even in physics because of conservation of energy. Okay, like when you have when you start from here, your kinetic energy is high, but your potential energy is low. Kinetic energy has something to do with the speed. Potential energy has something to do with the height. As we go up, okay, as you go up, what happens is at this point here, your potential energy is the maximum, yet your kinetic energy is the minimum. Okay, now then when it goes down, you trade that back. Then what happened here is your potential energy is minimum because the height is now 0, but your kinetic energy is maximum. In fact, it should be the same to where you started from. Okay, now I once have a misunderstanding. So Thomas, when you say the kinetic energy is minimum here, are you saying at this point the stone or the projectile actually is not moving, the velocity is 0? No, it's the velocity is not 0. Okay, the velocity is not 0. The vertical velocity is 0, but the horizontal velocity is still constant. So at this point, the velocity is actually v naught cosine alpha comma 0. Okay, that's the velocity at that point. In other words, the minimum speed of that projectile at any time, okay, the minimum speed happens when it reached the maximum height, and at that maximum height the speed is v naught cosine alpha. Okay, I hope that explains why when you have a tank, right, the mussel angle is at most 45 degrees. Why? Because if the angle is more than 45 degrees, like let's say 50 degrees, right? Okay, it may reach a higher point. Okay, it reached a higher point, but the horizontal speed at that time, it's too small because the angle is too high. The initial alpha is way too high. Okay, notice that a tank is being constructed as a surface-to-surface weapon. Okay, a tank is usually not being used when you need to shoot something in the air. Okay, you should, and usually not something in on the sea either. You use tank to shoot something from the surface to the surface. Okay. So let me say it this way. For the things that I didn't have a chance to talk about further, like at height at y equals to some height, okay, at the height equals to some height, then the velocity okay, maybe I should say the speed, okay, as long as it has the same height, y equals to height at the same height at t1 and t2. So basically I'm saying that it reached this height at t1 and the same height again at t2. Okay, the velocity at t1 is equal, the speed at t1 is equal to the speed at t2. In fact, we can say further that the v component, the x component of the velocity are the same. And the y component of the velocity are opposite. Okay, one of them facing up, the other one facing down. Okay. Now, how do we find the angle then? Suppose we want to shoot something in the air, right? And you shoot it here, okay, at T1. Can we find what is the angle of impact? So when your stone or your projectile happen to hit that drone, for example, you hit that at what angle of elevation? Okay, and the angle of elevation, angle at time t, will be equals to the y component over the x component. Basically, you create this guy and this guy, give you the tangent. So that will be the tangent inverse of this guy. That's the tangent inverse of that. This is the phi y component at time t, and this is the phi x velocity, x component of the velocity at time t. Okay, so suppose that is a drone, right? And it will be best if you hit that like at this angle here. So try to manage it in a way that you can hit it at that angle. Okay. Usually we don't have that privilege though. We can hit that, we'll be happy already, right? Okay, but if you want to know at what angle I will hit that, what is the velocity, that's what we're basically doing. Okay, now I have approximately 10 to 14 minutes left to do problems regarding this. Let me do one. Okay. Let's start with, for example, a shell is fired from the ground. So the initial height is 0. With muzzle speed 800 feet per second. With angle with alpha equals to, let's say, 30 degrees. So imagine you actually shoot that at angle of 30 degrees. So we expect this will be the trajectory. Okay, and then the initial velocity, initial speed is 800 feet per second. Can we find the trajectory? The trajectory RT will be initial speed 800 times t times cosine 30 degrees. The y component will be initial speed times t times sine 30 degrees minus 1/2 gt squared. Okay, now suppose that's what we have, then we ask ourselves, what is the range? The range will be phi naught squared sine 2 alpha over g. The phi naught is 800 sine 60 degrees over g, 800 squared. So that's how far it will go. Suppose, just for sake of simplicity, let g equals to 10. I'm sorry, is it 10? The g is 32 because it's a feet per second, huh? It's in feet, so that will be 32 feet per second square. Okay, so we will end up with 64 with 4 zeros, sine 60 degrees radical 3 over 2 over 32. So I get, what's that, 10,000 radical 3, 10,000 radical 3 feet. Okay, that's the range. The challenging part is, yeah, that's the range. How about the angle? How about the angle when it hits the ground. From the theory that we have earlier, well, the angle will be symmetry with the angle that it starts, right? It will be at 30 degrees also. Okay, in other words, it will land here at 30 degrees. Okay, when it impact with the ground. Okay, now let's do some challenging part. What challenging part? The challenging part is suppose a target is located at, let's say, coordinate 7,000 feet in the x direction and 200 feet high. Okay, find the angle where you should shoot that missile or shoot that projectile, shoot that shell. Okay, so the question is basically, if you have something in the air like this and the coordinate is 7,200, 200, okay, at what angle you're supposed to shoot it? At what angle you're supposed to shoot it such that it will hit that? What is the alpha? Well, the muscle, the angle of elevation we can change, but the muscle speed we cannot change, right? Okay, so the muscle speed, the V naught, still 800, but the alpha is the one in question. Okay, that's what we ask. Now, what is the trajectory? The trajectory will be 800 t cosine alpha, comma 800 t sine alpha minus 16t squared. What we will do is we will set this equals to 7,200. Okay. In other words, from the x component, we need to find the time and the alpha. So we have two variables here to make it 7,000, right? And we also have two variable time and alpha in the y component to make it 200. Okay. Now the question is, have you learned before how to solve this? Have you learned how to solve this? What we will do is honestly, I don't really know how to do this. Don't really know how to do this. I know these things though. I can work on the first one. It's a 800t is equals to 7,000 over cosine alpha, right? Okay. In other words, in our second equation, we can change this part become 7,000 over cosine alpha sine alpha minus 16t squared equals to 200. In other words, 7,000 tangent alpha minus 16t squared equals to 200. But I don't think it will help us in any way. Unless we go further, saying substituting the t. The t is 7,000 over 800 cosine alpha. So t equals to cancel two zeros. That's 35 over 4. 35 over 4 secant alpha. Okay, so plugging that in, 7,000 tangent alpha minus 16 times 35 squared over 16 secant square alpha equals to 200. In other words, I need to find the angle such that this statement is true. 35 squared secant alpha equals to 200. Okay, I suppose you are able to do this on your own. Yeah. But let me give you more steps. I will rewrite that secant squared alpha as tangent squared alpha plus 1. So that I have 7,000 tangent alpha minus 35 squared. I don't know what's that. Tangent squared alpha minus 35 squared equals to 200. Basically, now I have a quadratic equation with tangent alpha. Okay, I think I can reduce by at least 5. Actually, by 25, I can reduce by 25. If I reduce by 25, I get 49 tangent squared alpha. Reduce by 25, that's 280 tangent alpha. Reduce by 25, 49 plus 8, that's 57. Now then tangent alpha equals to negative b plus minus square root of b squared minus 4ac over 2a. Yes, there are two angles. So apparently one angle is this one, that's the largest angle, and the smaller angle will be the one shooting it directly, like that. Okay. Should I use my calculator? Let me do it. I still have little time. So I use calculator to help me. Let me share with you. So 280 squared minus 4 times 49 times 57. By the way, if you find that the discriminant is negative here, it means there's no way you can shoot that target. Okay, basically if you have a negative value inside the square root, that means whatever the angle, you will not be able to shoot the target. Okay, it's outside of your reach. Anyway, that will give us tangent alpha equals to 280 plus minus square root of what's that, 67,228. 67,228 over 98. Actually, we can reduce this a little bit. Okay, but I think what I will do is just to say that alpha 1, the first angle, is tangent inverse of 280 plus square root of 67228 over 98. That's the first angle. The second angle is the negative part. It's 280 minus square root of 67228 over 98. Okay. What is 67,228? The square root of that though. Let's see. The square root of this guy is 259,284. 259.284. Okay. And yeah, again, you just use calculator from there. Okay, I believe you can continue with the computation yourself, right? What I'm afraid is like you are already in calculus 3, but you still don't know how to solve this kind of equation. You don't even know how to set it up. That's sad, okay? While if you want to get hired in a place where you can shoot down a satellite, you can intercept an incoming missile, you're supposed to know this, right? Okay, don't tell me that, oh, Thomas, just use computer, because somebody needs to program that computer to do it for you, okay? Don't rely on artificial intelligence, because our defense is actually very weak if you rely on artificial intelligence, okay? You may think that's smart, right? No, somebody can actually jeopardize our artificial intelligence, and suddenly you don't get the answer that you're supposed to get if it were actually running normal. Okay, yeah, well, anyway, so we will get these two angles here. Of course, on the other hand, please make sure that this number here is less than 280, right? Because if it is more than 280, then the angle will be negative angle. That's kind of strange, right? In that case, then you will have only one value. Okay, the suggested homework from here is from 13.4, from 3 to 27, and then 37 to 41. Okay, then I stop here.